Hello everyone, Assalamu alaikum. Welcome back for another video in the series. In this video, let's now take a look at the same thing as we did in the previous video, but now I am using the MNIST dataset because I already showed you the MNIST dataset in the lecture in the previous videos. So just for the completeness, we will actually be working with this more when we talk about multi-layer perceptrons in future. So what's new now is I'm using a data loader, and this is usually how we load images in PyTorch on other types of data. So here are just some settings for my model, and here the MNIST dataset is already provided in the library called Torch Vision. It comes with a number of datasets. So if you install PyTorch, it will also if you use installer via the website, it will automatically install Torch Vision. So you don't have to install it separately. It usually is included in the command that you executed when you install PyTorch. So we use this MNIST dataset from Torch Vision from the datasets submodule. This is just specifying where to store the data. It will create a data folder in the next to my notebook here, because I called it data, but you can actually change this to whatever you want to desktop data or something, just where it keeps the data so temporarily. Then it has a test and training set. This is for testing. MNIST doesn't have a validation split, but I will show you in the multi-layer perceptron lectures how we can also create a validation split for that one. This one to tensor is kind of required. It's because MNIST is images and they come in, I think it's pill Python imaging library format, and you want to convert them to PyTorch tensors. So this one is converting the image representation in PyTorch to a PyTorch tensor representation. But we will also see later we can use other or data augmentation here, like randomly flipping or cropping images. So we will be talking about that a lot more when we talk about convolutional neural networks. Also, I should say that 2 tensor normalizes the pixels to 0, 1 range, so it's dividing them by 255. So I should mention that we don't have to do our data normalization ourselves. Of course, we could actually do something better. We could standardize them for color images. Sometimes people standardize using the mean and standard deviations from ImageNet. We could technically also do that for color images. For here, something like MNIST, it doesn't really matter at all because they are black and white images. To be honest, there's probably no difference in the performance of the model because it's a very simple optimization task with stochastic gradient descent. So this is defining the training data set. This is defining the test data set. The difference is really that we set train false and here to true. We only need to download it once, right? So we don't have a download here. Then we use the data set. We define the data loaders. Here I'm defining a data loader for training set. I can set my batch size. That's my mini batch size. I set it to 256, and then whether we want to shuffle or not. So this is shuffling before each epoch, shuffling the data set. Notice that here I'm not shuffling the test set because it doesn't really matter. I'm loading the test set in batches. It's also not really necessary because we don't do any training in stochastic gradient descent on test set. But in, let's say, if we work with the real image data sets like ImageNet, the test set can be quite large and it might not fit into memory. So we can also load it one by one. Basically, that's what I'm doing here. Uh, f- for just for completeness, this is more like for verifying that everything looks good. So here I'm just having a for loop over the images and labels in the training loader, just to make sure everything looks okay. And you can see it's loading the images in this NCHW format. The batch size, the number of color channels. We only have one color channel here because MNIST is black and white. And then we have the height and width here. And the labels, of course, are a vector because that's just the numbers. These labels are not one hot encoded, so you can see that they are just the numbers of class labels, the 10 class labels. It's not necessary to one hot encode them because PyTorch does it automatically when we call the cross entropy loss. So here's now my implementation. This is the same as in the previous video which I did from scratch. So there's nothing really different. Same thing. So also notice the accuracy. I'm computing it using a for loop over the data loader. I don't have to go through this. I think this is something you could copy and paste if you need it. So the interesting part, what I wanted to show you is because I don't want to make this video too long. I don't want to spend too much time on things that are not that important right now. So the important parts are here that we are concatenating. Our image looks like it's a 3D tensor. One image is a 3D tensor 28 by 28, and then the color dimensions. So if you don't think of the color dimension, it would be a matrix, a 28 by 28 matrix. But we need a feature vector as input. So we would concatenate it to a very long vector 28 times 28. So it will be 784 dimensional vector. So that's what I'm doing here. I'm concatenating it into a long vector. I can maybe show you that how that will look for like for one given. Let's say we take one image, so this would be the one color channel by and 28 by 28. So you can see now it's a one long vector basically. So in this case I think it's a matrix because we have the first dimension, but but the same thing applies. All right. And then we call our model. Notice when we use PyTorch, we don't use dot forward because it's actually better to just call it like this. It will internally call forward, but it will do the same, do some extra checks before it calls this forward method, as I explained in an earlier lecture. And now the interesting part is we compute the cross entropy cost or loss here, and notice that it's important that it uses the logits as input. So it's not using the probabilities, it's using the logits. So we have to pay attention that we provide the logits and not the probabilities here. And then this we zero the gradients to backward, or we are just averaging the costs. So then I'm plotting it. So this cost is the average cost per epoch, and now this is how the loss looks like. You can see that it goes down as expected. Let's take a quick look at the test accuracy. It's actually pretty good. I mean, given that this is an image dataset and we only have a linear classifier, we don't even use a neural network, I mean a multi-layer network, we already get a pretty good performance. And personally, I also recommend you, when you work on classification tasks, always to run a logistic regression classifier as well, or softmax regression classifier as a baseline, just to get a feeling of how difficult the classification problem is. So if you train, let's say, convolutional network, and you have got only 94% with the convolutional network, you would say, okay, this is such a complicated convolutional neural network, why does it only get 94% when I get already 92% with logistic regression? Maybe my model with 94% isn't that good after all. So it's always a good thing to run also logistic regression as a baseline. Here's just an example, learning three random images from the dataset, and then I'm doing my predictions. So calling this one on the feature vectors, and then the argmax to get the class labels, because this one would give us just the probabilities. You can see we are taking the argmax. So in this way, we compute the class labels. So with that, this is all I think I have for this from scratch implementation using this MNIST dataset. I hope this was helpful. If you have any questions, feel free to drop them in the comment box below, and I'll see you in the next video.